These are the solutions to quiz number 1. Okay, so the first problem. The figure shows the position of an object here at 1, 2, 3, 4, 5, 6 seconds, moving along a straight line. Which of the following statements about this object is true over the interval shown? So you notice that the object is moving to the right, and it's slowing down because the spacing between successive points is getting smaller. So the acceleration is opposite to the direction of motion. It's going to the left. Okay, so the object is accelerating to the left. The next problem. The graph shows the speed of a car traveling in a straight line as a function of time. The value of Vc here is 3.90 meters per second. Vd is 6.60. Counted the distance traveled by the car from 1.5 to 6.0. So the distance traveled, the displacement, will be the area under this curve. So the area of this rectangle here is 1.5 times 3.9 the height. That comes to 5.85. The area of this trapezoid, you take the average of the base okay, so I'm turning it on its side. You take the average of the base and the top. All right, average of the base and the top is 5 points. Okay, so it's 3.9 plus 6.6 divided by 2 to get the average of the base and the top, times the height, which is 2. It's coming to 10.5. Now the area of this rectangle is 1 times the height, which is 6.60, and that comes to total, when we add them all together, 22.95. So that's the distance traveled. Number 3, you're driving at 95 kilometers per hour. How many meters are you covering per second? Okay, so this is just a straight conversion of kilometers to meters. So kilometers is 1,000 meters. Hours is 3,600 seconds. Plug that in here, plug that in there. You get 26.4 meters per second. If t is time, x is length, v is velocity, and a is an acceleration, which of the following expressions could be valid? Okay, the units have to make sense. So the first one is meters times seconds plus meters over seconds. That's no good. Second one is meters, and then we have meters per second times second. This is okay. They're both meters. The rest don't make any sense. This is meters per second times second, and then meters per second squared for acceleration. And then VA is meters per second times meters per second squared minus something else in seconds. That's no good either. And then acceleration over time, that's meters per second divided by meters per second squared per second plus meters, and that's no good. Go on. So two objects have dropped from a bridge in an interval of 1.0 seconds apart and experience no appreciable air resistance. As time progresses, the difference in their speeds. So these are plots of their velocities versus time. You have just a straight line like this, okay, because the velocity is negative, the y-component of velocity is negative. And then for the other object, it starts at 1 second from S, and then it also goes down. Okay, so they both have the same acceleration, that's why they're the same slope. Now if you're talking about the actual difference in their velocities, you see that the difference in the velocities at any given time remains the same. Okay, so the difference in speeds remain constant after 1 second. Next problem. An airplane has a takeoff speed of 55 meters per second. Assuming constant acceleration of 1.71 meters per second squared, what is the minimum length of runway it needs for takeoff? So we don't have any delta t in this problem, so a good equation to use is v final squared minus v initial squared is equal to 2a delta x. We can know all these except for delta x, so we can have, say, delta x is v final squared minus v initial squared over 2a. So it's 55 squared minus 0 squared divided by 2a, a is 1.71, and we get 885 meters. Next problem, how long is the airplane accelerating down the runway? We know the final velocity is 55, the initial velocity is 0, P final is equal to V initial plus A delta T, so A is 1.71, T is what you're solving for, okay, so T is 32 seconds. Okay, if the airplane had double the acceleration, double the necessary takeoff speed, how long would the runway have to be? Okay, so let's figure out what we solved for. Up here, we had initial speed was 0, so we can just ignore the initial that starts from 0. So we have v final squared over 2a is the delta x, the formula for delta x. So delta x is v final squared over 2a. So now if we have a new runway, we have v final for the new case squared over 2 times the new acceleration. But we say the new takeoff speed is twice that of the original, so it's 2v final. And then the acceleration is 2 times the original. So we have 2vf quantity squared, so it gives me a factor of 4. And then we have 2 times 2a here, so we have v final squared over a. Now let's go back to what this one was. So this new one is factor 2 bigger than delta x that we had before. So it's twice the length. Okay. Next problem. Find the magnitude of minus a plus b, where a is 20.1, 64.7, b is 90.3, minus a negative 144. Okay, negative a plus b, so we just need to flip the signs on a and add components with b. So negative 20.1 plus 90.3, negative 64.7 plus negative 144. Adding the components together, you get 70.2, negative 208.7. The magnitude is the square root of 72.2 squared plus negative 208.7 quantity squared. The square root is assigned over the top of them, and then we get 220.2. Last problem. Find the direction of a minus a plus b, where a is the same as we had before. Express the angle counterclockwise relative to the positive x-axis. Okay, so let's make a plot. The components we said were 70.2 and negative 208.7. So 70.2, negative 208.7. So the vector is pointing like this. It's an angle that's bigger than 270 degrees. So now we can calculate the tangent of theta. Tangent of theta is the y component over the x component. That's negative 208.7 over 70.2, or negative 2.97. So now we punch this in the calculator, and theta is equal to negative 71.4 degrees, or 108.6 degrees. Okay, but if we're going to write this as an angle greater than 270, we add 360 to the answers here. And the correct one is 360 minus 71.4 is 288.6. That gives the proper angle.